Okay, in this video we're going to be looking at measures of position and outliers. Um, and so we're going to introduce and determine the idea of what's called a z-score. We're going to look at percentiles, determine and interpret what are called quartiles, the interquartile range, and then outliers. It's quite a few things to get through in this lesson, but we'll be using several of these things, especially the z-scores, frequently throughout the rest of this course. So in section 3.1 we determine measures of central tendency, which describe the typical value in a data set. 3.2 we looked at dispersion, that was our standard deviation, okay, which was telling us about the spread in a set of data. Okay, now in this section we're going to discuss the measure of position, which describes the relative position of a certain data value within the entire set. Is it towards the top, towards the bottom, in the middle-ish, lower middle? Where's it at? Okay, so first we're going to look at this idea of a z-score. And we'll start it off with an example. Okay, so at the end of the 2014 season, the Los Angeles Angels led the American League with 773 runs scored, while the Colorado Rockies led the National League with 755 runs scored. Now it appears that the Angels are a much better run-producing team. However, this comparison is unfair because they play in two different leagues. Okay, in baseball, you have one league has what's called a designated hitter where they hit for the pitcher, and in the other league, the pitcher has to actually bat. So in this case, the Angels play in that American League where the designated hitter bats for the pitcher. The Rockies play in the National League where the pitcher must bat, and to note, pitchers in the major leagues are typically poor hitters because they spend the vast majority of their time practicing on pitching and then recovering and so forth. So to compare the two teams' scores of runs, we need to determine their relative standings in their respective leagues. So, for example, how does the Angels compare to all the other American League teams? How do the Rockies compare to all the other National League teams? And then we'll create what's called a z-score that allows us to compare kind of different data points, and it brings them to the same level to compare. So coming from two different groups, and then we're going to kind of normalize it so we can take a look at it. So the z-score represents the distance that a data value is from the mean in terms of standard deviations. Okay, so if you get a z-score of 1, that means you're exactly 1 standard deviation above the mean. If you get a standard deviation of -2, for example, that means you're 2 standard deviations below the mean. That's what a z-score is going to tell us. It's how many standard deviations is a score away from the mean. Okay, the way we find it is subtracting the mean from the data value and then dividing that result by the standard deviation. And they're, for population and for sample, they're the same. So x minus mean over sigma, so the data point minus the mean over standard deviation, or x minus x bar over s. Same whether we're population or sample. Now, a z-score is unitless, and the nice thing about it is when we look at z-scores, the mean is 0 and the standard deviation is 1. So again, the z-score that you get tells you how many standard deviations you are away from that mean of 0. Okay, so here's a question. So we have babies born after a gestation period of 32 to 35 weeks have a mean weight of 2,600 grams. Okay, so that's the mean. And they have a standard deviation of 660 grams. Babies born after a gestation period of 40 weeks have a mean weight of 3,500 grams, which should not be surprising if they're in the womb longer, and a standard deviation of 470. So suppose you have a 34-week gestation period baby that weighs 3,000 grams, and then you have a 40-week gestation period baby that weighs 3,900 grams. We want to find the z-scores to figure out, which baby is bigger or smaller? Where do they lie within their appropriate data sets, and then how do they compare to kind of the norm within each? So I'll just say the mean for the first one was 2,600 grams, and the standard deviation, well, let's just say S1, the first standard deviation was 660. For the second group, that mean was 3,500 grams, and the standard deviation was 470 grams. So our z-scores for the first baby, okay, the first baby weighed 3,000 grams. That was a 34-week. So we take 3,000, then we minus the mean of that group, which was 2,600, and then divide it by 660. Okay, and when I calculate that out, I get 0.60, repeating. So it's about 0.6 standard deviations above the mean. Now, when I look at the baby that was more than 40 weeks, okay, that baby, let's see, had a weight of 3,900 grams, and then I subtract the mean of 3,500 for that group divided by the standard deviation of 470. And notice, each of these are exactly 400 grams above the mean, but the standard deviation for the second group is smaller at 470. So here I get a z-score of 0.85. Okay. So now we have the z-scores, and which baby weighs relatively less. Okay. In this case, the 34-week baby weighs relatively less because it has a smaller z-score. So the 34-week baby is 0.60 standard deviations above the mean. The 40-week is 0.85 standard deviations above the mean, which tells us that relative to the group, the 40-week weighs a little bit more than the 34-week. And that's what his z-score tells us. So it brings us down onto the same level. Okay. Now let's look at batting championships. Okay, we've got the highest batting average ever recorded in Major League Baseball was by Ted Williams, and this was in 1941, where he hit a pretty significant 0.406 or 40.6% of the time. That year, the mean and standard deviations, 0.2806 was the mean, the standard deviation was 0.038. In 2014, Jose Altuve was in the American League batting champion. He was the American League batting champion with an average of 0.341. And in 2014, the mean and standard deviations were 0.2679 and 0.0282 for the standard deviation. So who was the better batter compared to their peers, Williams or Altuve? So what we're going to do is, again, different years, different players, and so we have different data sets, so we need to get them on a level playing field. So we're going to find the z-score. So the z-score for Ted Williams, okay, his batting average was 0.046 minus the mean that year, which is 0.2806, and then divide that by a standard deviation 0.0328, and we get that Ted Williams had a z-score of 0.382, which is 3.82 standard deviations above the mean, which is very significant. Okay, now we'll look at Jose Altuve. His batting average was 0.341 or 34.1%, and then minus the mean 2 2.2679. So you can see that the groups definitely were not the same in the means. So that's why we're getting a z-score to compare apples to apples. And there's less dispersion because you have a smaller standard deviation during the time of Jose Altuve. So I'm going to divide by that standard deviation, and I get a z-score of 2.59. And notice Ted Williams, his average is significantly higher, or excuse me, his z-score is significantly higher than Jose Altuve. And we can see just how extreme it was for Ted Williams compared to Jose Altuve. So Ted Williams had the better average compared to his peers. So that says average compared to his peers. Because again, higher z-score, so he was almost 4 standard deviations above the mean, whereas Jose Altuve was 2.6, almost 2 3/4 above the mean. So pretty impressive for Ted Williams. Okay. So this will be the last question for this video, but we have school admissions. So we have a highly selective school, or boarding school will only admit students who place at least 1.5 standard deviations above the mean on a standardized test that has a mean of 200 and a standard deviation of 26. And we want to know what's the minimum score the applicant must take or must score in order to be accepted. So that 1.5 standard deviations above the mean, that is a z-score. And so we want to find out, what's the actual score. So remember, the z equals, and if we're looking at our population, it would be x minus the mean over the standard deviation. Well, we know the z-score we want is 1.5. We don't know the test score, so that's what we're trying to find, but we know the mean, and we know the standard deviation. So now we have a basic algebraic equation to solve here for x that will tell us the minimum score that is needed. So to solve this, I would multiply both sides by 26, so I had 1.5 times 26 equals x minus 200. And then I'll add 200 to both sides, so 1.5 times 2.6 plus 200 equals x. And if I multiply and then add, that's 239. So the minimum score that an applicant must score to get into this boarding school or to be considered to be accepted is a 239 on a scale where, again, the mean is 200 and the standard deviation is 26. And if you think about it, 239, if our standard deviation is 26, well, if I want to be 1.5 standard deviations above the mean, then I would take 26 and times it by 1.5, and that would give me 39. And then if I take 39, add it to the mean, that will be 239. So, if you kind of think through it logically, that's another way of doing it. But this is just kind of the general form. Here's the equation. We can substitute things in and just rock it off from there. So we'll pick it up in percentiles in the next video.